In this lesson, we're going to start talking about how we can prove triangles congruent. Now, in the last unit, we defined what congruence was, and we defined it by saying things are congruent, meaning that there exists a composition of basic rigid motions that maps one figure to the other. And what we did is we stated the rigid motions that mapped, and then we wrote out each thing that was congruent to everything. So we wrote out the angle congruencies and the side congruencies. Well, we don't want to have to do that. We don't want to have to name every single piece that's congruent. So we want to come up with some shortcuts. We want to figure out the minimum amount of criteria so that we can prove triangles congruent. And there are 5 different theorems to go through. We're going to go through one of them today. So we're going to start with what we call the side angle side triangle congruence, SAS. So, and it states this: two pairs of sides, if 2 pairs of sides and the included angle are congruent, then the triangles are going to be congruent. So if I have these markings here, I have triangle ABC and A prime, B prime, C prime. You can see I have 1 pair of sides, 2 pair of sides, and the angle in between the two. That means that I can say triangle ABC is congruent to triangle A prime, B prime, C prime. Remember, the correspondence is important. A corresponds to A prime, B to B prime, C to C prime. But we're going to talk about how we can show this with rigid motions next. So this just points out that we can map one triangle to the other using a series of rigid motions. And there should be a little triangle symbol. I know it's on your paper, but it doesn't seem to show up in here. Okay, so let's start off. The 2 triangles are separated out in space, and I use a translation to map A prime to A. And there's my translation vector, A prime A, in this case. Once those 2 are together, that maps them in the same spot. I can rotate segment AC prime, or C double prime now, over to C. And that's going to line up these 2 sides. So once I do that, I have what I have here. So they're lined up, the A's are in the same spot, the C's are in the same spot. And then if you look at this, I can reflect B triple prime over line AC, and it's going to map to B. Here's why. Let me take another step back. The translation is easy. I can move any point to any other point. C double prime is mapping up with C because these 2 side lengths are the same length. See that with the double marks there? So I know that C double prime is going to be at the same spot that C is. So when we look at the reflection, A is lined up with A, C is lined up with C. If I reflect B double prime, because these 2 angles are congruent and these 2 lengths are congruent, that means that B triple prime has to end up at B. And then everything's going to line up. If I want to write this out as a transformation, the first thing we did was to translate from A prime to A. And then we rotated about point A a certain number of degrees, I don't know what. And then we reflected over line AC. We applied all that to the original triangle A prime, B prime, C prime. So doing all that, a translation, a rotation, and a reflection showed that I could map a triangle onto another and show that they are congruent only by given 2 congruent sides and the included angle. But sometimes I don't have to do all 3 steps. Here, if they share a side, well, this side's already locked in place. The angles are congruent, and these sides are the same. So if you think of what's the one rigid motion I need to map B triple prime to B, that's going to be a reflection across AC. That will map B prime, triple prime to B, because reflections preserve length and angle measures, so that's going to make them congruent. If they just share a vertex, then I would need a rotation and then a reflection. So this would be a rotation about A and then a reflection over AC. So sometimes you don't need all three. Sometimes you just need one or maybe two out of the three rigid motions. But you can do everything with at most three. So before we start proving triangles are congruent by using some theorems instead of rigid motions, there's a couple things that we need to remember, and these are very important properties when we do triangle proofs. The first one is the fact that vertical angles are congruent. And we can recognize vertical angles by the bow tie looking thing. They are the angles formed when lines intersect. So in this case, those two angles would be considered congruent. Angle KLJ is going to be congruent to angle MLN. And then another very common property that we use quite a bit is called the reflexive property. And that says that a length is congruent to itself. I know it sounds silly, but in a triangle proof we have to label everything that's congruent. So AC is congruent to AC. Those two properties are going to be very important when we do triangle proofs. So the triangle proof that we are working on today is the theorem that says two sides and the included angle, if I have two sides and the included angle congruent between two triangles, that is sufficient. Having that amount of information, that is sufficient to prove triangles congruent. But I don't want to write all that out. So instead, what I write is side angle side is congruent to side angle side. That's my side angle side triangle congruence. We just showed that through rigid motions. A translation, a rotation, and a reflection maps the two triangles onto each other. That's all I need to show that they are congruent. So here's our first triangle proof. When you're given a proof, you're going to be given a set of things to start with, and then you're going to be asked to prove something else. So here's the beginning part. Given, in this diagram over here, angle LMN is congruent to angle LNO. I'm missing my little angle symbol there. And MN is congruent to ON. I want to prove the triangles are congruent. So to do that, we're first going to mark up our diagram. If these two angles are congruent, L and M is this one, and L and O is that one, you're going to mark it up. And then MN is congruent to ON. Well, what I need to prove these two triangles congruent are two sides and the included angle. So that really tells me what sides I need to get. I have one pair of congruent sides. I have the angle, so the side I have to get is LN, because that's going to give me side, angle, side. I can't use LM and LO because that isn't side, angle, side. You have to have the two sides that create the angle. So here's how we write a proof. We always repeat our given. Angle LN M is congruent to angle LNO, and MN is congruent to ON. That's what I'm given. All right, well, I just showed you a property before that says a segment is congruent to itself. So I can say LN is congruent to LN. And that was the reflexive property. So there's the reflexive property. That's enough to say that the triangles are congruent. I can say triangle LMN is congruent to triangle LON because I have side, angle, side congruence. So that is side angle side is congruent to side angle side. And your proof is done. It was a 3-step proof. That wasn't too bad. Down here, describe the rigid motions that would map triangle LON onto triangle LMN. Well, let's look. LON, if I'm going to map that, they already have a shared congruent side. So it's one step. I'm going to reflect the triangle over LN. And because these sides are congruent and these angles are congruent, that means O is going to map to M. So it's just a reflection. So a reflection is little r over ln of triangle LON, and that's going to map it to triangle LMN. So let's try another one. We have what we're given in this diagram is angle HGI. HGI is congruent to angle JIG. So I'm going to mark those up, HGI and JIG. And then I also have that HG is congruent to JI. And I want to prove the two triangles are congruent. So I write my given, angle HGI is congruent to angle JIG, and HG is congruent to JI. That's given. We always write down our given. Well, again, I need to get side angle side. So if you look at this, once again, I have side and angle, and the side I need to get is the shared side, GI. So I can say GI is congruent to itself. And that's the reflexive property. So that's him. That's enough to say the triangles are congruent. Triangle HGI is congruent to triangle JIG because of side angle side congruence. Now, if I want to describe the rigid motions that maps JIG to HGI, it can't just be a reflection, because if I reflect J, he's going to end up here. So there's a couple things you could do. I could do this, there's several ways actually. It could be 180 degrees around the midpoint, or I could translate and I could move him over here and then rotate 180 degrees. So I could look at a translation of JI. And that's going to map J to I. Then a rotation of 180 degrees about point J. And that will map the one onto the other. So I've skipped over example 4. We're going to do that one together in class. And I'm going to finish with example 5 here. Given this diagram, SU and RT bisect each other. And I want to prove that triangle SVR is congruent to triangle UVT. SVR. So these are like the side triangles. I want to prove that this little guy is congruent to this little guy. So a couple things first. When I say that SU and RT bisect each other, first of all, these are segments, they're not angles. So do not say that the angles are bisected. These are line segments. They are cutting each other in half. So when I put that down, SU and RT bisect each other. That's our given. Each other. So that's given to us. Let's mark up our diagram to show that. They're both being cut in half. So I'm given that. Once you have your diagram marked up with what you stated, take a look at it and see what we can find. Remember, we want to find side, angle, side. So if we look at our diagram and I'm trying to get these two triangles congruent, I have to get the angle in between them. So what kind of angles are these? Hopefully, you can see that they are vertical angles. And vertical angles are congruent. So angle SVR is congruent with angle UVT. Vertical angles are congruent, which means I can mark that up. Now I have my side angle side criteria. So triangle SVR is now congruent to triangle UVT. And that's by side angle side. And I'm done. If I wanted to describe the rigid motions, you have to be careful. A reflection will not work because if you reflect through V, T is not going to map to S. T has to map to R. So instead, a rotation of 180 degrees about point V would work. So a rotation of 180 degrees about V. So that would be a capital R with a little v, comma, 180. That would map triangle UVT to triangle SVR. So we will do more of these examples in class. The best way to learn proofs is to muscle through it and try them, and lots of practice.